In this lecture we are going to do the analysis of the vapor compression refrigeration systems. Okay, so we are going to analyze for each and every processes for 1 to 2, 2 to 3, 3 to 4, and each and every processes we are going to analyze. So the first process which we are going to analyze is 1 to 2, that is isentropic compression. Okay, the process 1 to 2 is now being analyzed. Okay, so to find out in this 1 to 2, the most crucial thing is what is going to be the amount of work that is been consumed by the compressor. Okay, that has been consumed by the compressor from 1 to 2. Now in the open system, now compressor is an open system. Okay, from there you have seen that, okay, the work that has been consumed by the compressor is nothing but it is going to be the enthalpy difference between the inlet and outlet. Okay, the outlet point enthalpy and the inlet point enthalpy, and take their difference. That difference is going to give you whatever is the amount of work consumed by the compressor. Okay, now the first thing, how can you find H1? How can you find H1? H1 is going to be very easy, because in steam table, in that particular, this is in saturated gaseous line. Okay, this is in saturated gaseous line. That means there are two, as I have told earlier, there are two segments in the steam table. Okay, one is saturated zone, one is superheated zone. So in the superheated zone, in the saturated zone, since this is in saturated gaseous line, okay, in the saturated zone, in that particular pressure we have taken two, higher pressure as 8 bar and lower pressure is 1 bar. Okay, let this is higher pressure is going to be 8 bar and lower pressure is going to be 1 bar. Okay, so at that 1 bar pressure, okay, from the steam table, in this saturated zone you are going to find a pressure of 1 bar. Okay, in that pressure you are going to find HF, HG, HFG, similarly SF, SG, SFG, everything you are going to find. Okay, so at 1 bar pressure, okay, at 1 bar pressure, this is the constant pressure line for a vapor dome. At 1 bar pressure, what is going to be the value of Hg? That is going to be nothing but enthalpy at point 1. Hg is what? Enthalpy at gaseous line. And Hf is what? Hf is nothing but enthalpy in fluid line. Okay, so if you find out Hp, you are going to find out the enthalpy at this Hf, you are going to find out the enthalpy at this point. You are going to find Hg. Okay, if you write the value of Hg, that means you are going to find the enthalpy of this point. This is Hf and this is Hg at that particular pressure, 1 bar. Similarly, at 8 bar pressure, for saturated region, for 8 bar pressure, okay, this point is going to give you Hg at 8 bar. Okay, at 8 bar, okay, whatever the value is there, at Hg the enthalpy value is going to be of this point, and Hf is going to be the value of this point. Okay, so this is the scenario. Now from 1 to 2, finding out 1 is very easy, because H1 is what? H1 is nothing but Hg value at EP. EP means evaporator pressure. This is evaporator pressure and this is condenser pressure. Okay, both are going to operate in constant pressure. Okay, so this is going to be evaporator pressure. H1 is nothing but Hg value at evaporator pressure. Now 1 to 2 is again reversible adiabatic process. Reversible adiabatic process means what? It is going to be isentropic process. That means entropy value at point 1 and entropy value at point 2 is going to be same. Now using that relation, we used to find the different other properties. Okay, S1 equals to S2. So using the dryness fraction formula, we are going to find the dryness fraction. After using the dryness fraction, we used to find the other enthalpy values or other values, other property values like enthalpy, internal energy, we used to find. Okay, but the concept of dryness fraction is only going to be there when the point where you needed to find the properties is going to be inside the vapor dome. Okay, if and only if the point is inside the vapor dome, then only the dryness fraction thing or dryness fraction concept will come. Okay, but not before that. So now entropy is same between point 1 and point 2. We are going to find the process of properties of point 2. That means what is going to be the enthalpy at point 2. Now that point 2 process, or the point 2, the state 2 is going to be out of the vapor dome. Since it is out of the vapor dome, its dryness fraction is always going to be 1. So dryness fraction is not going to be the concept here with which we can find the enthalpy value at point 2. We have to attain, or we have to attempt one different process to find out the enthalpy at point 2. If this point 2 was inside this inside the vapor dome and it had a isentropic value of this at this point, then we could have easily finding out the dryness fraction. Okay, since the dryness fraction concept is not going to be applicable here because the point 2 is out of the vapor dome, that's why H2 is going to be superheated, enthalpy at superheated zone. Okay, so how can you find out? So you can see S1 is going to equal to S2, but S1 is one in saturated segment. S1 is in saturated segment. Okay, it is in S1 is in saturated gaseous line, but S2 is what? S2 is in superheated zone. S2 is in superheated zone. Superheated zone means if you further after converting the total liquid into gaseous part, after if you further heat that steam, then this is going to be superheated. Okay, so S2 is going to be in superheated region. Okay, so what can you do? You can go to the superheated segment. Okay, you can go to the superheated segment of steam table. Okay, for finding out the H1 we are going to the saturated region. Okay, now to find out the point at H2 we need to go to the superheated region. In superheated region, at some particular pressure, okay, a temperature, at some particular temperature you are going to find the value of S, H, U, V, all the values you are going to find. Okay, now the pressure they have mentioned, that is already is going to be 8 bar. Okay, so in saturated region you go to the segment of 8 bar. Okay, for 8 bar there will be different temperatures and different values. Okay, so there will be some S value, S value, S value, S value. Now whatever the value of S1 is going to be equal to S2, whatever the value of S1 is going to be equal for S2. Okay, now this is the superheated region. At 8 bar pressure there is going to be a S value which is going to match with this value. Okay, there in this S column there is going to be a value which is going to be equal to this S value. Okay, that means in superheated region whatever the entropy value of this point is going to coincide with one of the values in the steam table. Okay, now after finding that value you are going to find the enthalpy value for that corresponding some temperature will be there. Okay, so for that value of entropy you are going to find the same amount of enthalpy. Okay, that means what? In the steam table going to the 8 bar you are going to search for the entropy value which you have found out for point 2. After searching it you are going to find a value. That value, and corresponding to this value there is going to be enthalpy value also. Okay, now that enthalpy value is going to be your enthalpy at that point 2. Okay, so what is H2? H2 is nothing but H is the superheated enthalpy at condenser pressure. This is the condenser pressure at condenser pressure and S2. Okay, with S2 this is going to give you the value of enthalpy of point 2. Okay, so likewise from steam table you are going to find out the value of H2. Okay, so once you have found out H2 and once you have found out H1 from the steam table, then what is going to be there? The work done by the compressor you can find easily. The work done by the compressor is now going to be what? It is going to be the difference between the enthalpies at the inlet of the compressor and outlet of the compressor, and this will give you the work that has been consumed by the compressor. Again, work done by a compressor is generally an open process. Okay, and it is going to be adiabatic. Okay, now in the open system work, okay, we have find out what is going to be the work done for an adiabatic process. Okay, now whatever the working fluid is going to be there, if they are mentioning that that particular air is there and and the adiabatic index is going to be this. Okay, that means what? For a particular gas that has been traveling throughout the working fluid that has been traveling throughout the machine parts, if they mention the gamma, and you have the privilege to know what is going to be the pressure at different points, pressure 1, pressure 2, volume 1, volume 2, then you can also find out the working pressure with the work consumed by the compressor with the help of this formula also. Because this is going to be what? Gamma by gamma minus 1, P2, V2 minus P1, V1 is nothing but this is going to be the open system work for adiabatic process, and compressor is an open system work and it is also going to be an adiabatic process. So this formula you can use if you know these things. Okay, if in question these values are given, then using this formula you can also find out what is going to be the work consumed by the compressor. Okay, so the second process which we are going to analyze now is going to be our 223, that is constant pressure heat rejection process. Okay, so we need to find out what is going to be the amount of heat that is going to get rejected. Okay, so again this would be what? This would be nothing but the enthalpy difference between these 2 points at point 2 and point 3. Okay, so now H3 is what? H3 you can easily find out from the saturated zone, because H3 is at saturated vapor line. Okay, saturated liquid line. Okay, now from this line, if you want to find out the enthalpy at this point, you are going to find for the pressure of 8 bar. At 8 bar pressure, what is going to be the value of HF? Okay, what is going to be the value of HF at condenser pressure or high pressure or 8 bar, which you have supposed. Okay, 8 bar, then this at this pressure, whatever the value of HF is there, is going to give you the value of H3. Okay, now from the first law of condenser, neglecting the kinetic and potential energy changes, what is going to be there? The work done or work consumed or work interaction in the control volume, CV means control volume, in the condenser is going to be 0. There is not going to be any shaft work, either input or output. Okay, so Q is going to be negative here. Why this? At first I have written the formula. Okay, now I am making the changes. So Q is going to be negative here because heat is going to get rejected. So once heat is going to get rejected, this would be negative. So Q would be what? It is going to be H2 minus H3. Okay, H2, that means enthalpy at point 2 and enthalpy at point 3. The difference will give you what is the amount of heat that has been rejected. Now, enthalpy at point 2 you have found out in the last process. While analyzing the last process, you have found out enthalpy at point 2, H3. We have seen how to find out. Now this difference is going to give you heat. So this is going to be the analysis of the second process. Now the third process is isenthalpic expansion process, because we are using a throttling valve here. Okay, now in throttling valve the enthalpy always remains the same. Okay, now this is a pH diagram. Okay, and the vapor dome goes like this. Okay, so from 1 to 2 it was compressor, 2 to 3 was rejection, 3 to 4. Okay, 3 to 4 is going to represent the isenthalpic process in pH diagram. Okay, 3 to 4 is going to be parallel to the P axis. Okay, so the only analysis is going to be here is going to be nothing but H1 is going to be equal to. Okay, so this is the only analysis we need. Okay, so that now this is needed, so that this is drawn in pH diagram, right? But if we draw a TS diagram, okay, TS diagram, we can find out the relations, or even in pH diagram also we can find out the relations in other relation. That means all the properties we are going to find out for or state 4 by using this relation, that H2 here H1 is going to be equal to, but this is the general formula, but for this case H3 is going to be equal to H4. Okay, H3 is going to be equal to H4, but this thing is needed, so that we can find the dryness fraction at this point. Okay, so that we can find the dryness fraction at this point, and after that we are going to find out. That means this thing, okay, whether it may be isentropic or it may be isenthalpic, these relations are needed so that we can find the properties by using this formula. That means we can easily find the properties from properties of point 3. Okay, we can easily find the properties of point 3 from steam table. But what about the properties in point 4? So to find the properties at point 4, we need a relation, that is the enthalpy of point 4 is going to be equal to the enthalpy at point 3. By this relation we can find out the other properties at point 4 also. So this is the only analysis which is going to be required for us, so that we can find out the different processes. Now from this analysis we know that H3, how can we find H3, and if once we find H3, H4 is also going to be found out easily, because they are having the same enthalpy level. Okay, now enthalpy at point 1 is already known, enthalpy at point 1 is already known, enthalpy at point 4 is already known, because this is going to be equal to the enthalpy value at point 3. So if you want to go for the 4 to 1 process, okay, so this is not 2 to 3, this is 3 to 4. This is 3 to 4. So if you want to go for the 4 to 1 process, what is going to be there? Okay, 4 to 1 is nothing but heat input process to the system. Now what is going to be the amount of heat input? It is again going to be the enthalpy difference, that is H1 minus H4. Now H1 you can find out from the enthalpy difference. Okay, now H4 is what? H4 is equal to H3. Okay, so that means H1 minus H3 is going to give you your whatever the heat input is going to be there in vapor compression refrigeration system. Okay, so Q in for this is H1 minus H3. So if you analyze from 1 to 2 and 2 to 3, that would be enough for you, so that you can find out the Q input. Okay. Okay, so now we are going to see what is going to be the COP for the refrigerator running in VCRS. Okay, so this is going to be nothing but RE by work input. RE means refrigeration effect. Refrigeration effect means what? What is going to be the heat input into the system from the space where you need to maintain the temperature. And this is going to be the heat out or Q out. Okay, so refrigeration effect is going to be what in this from this analysis what you have seen. What is going to be the refrigeration effect? Refrigeration effect is nothing but this Q in. Q in means what is the amount of heat that is being taken out from the space so that we can maintain the temperature. Okay, so refrigeration effect is going to be what? Nothing but Q in. And what is going to be the W input? W input is nothing but work done by the compressor. Now from this, what is Q in? What is Q in? Q in is nothing but H1 minus H4. Okay, H1 minus H4 is going to give you your Q input, okay, or refrigeration effect. And what is the work done by compressor? It is nothing but H2 minus H1. H2 minus H1 is going to give you the work that has been consumed by the compressor. So this is going to be your COP. Now in this place you can also write H3, okay, or H4, because H3 and H4 is going to be same for vapor compression refrigeration system. Okay, so you can write either of H4 or H3, and this will be your COP. Okay, now another thing we need to remember, that the refrigeration capacity is nothing but mass flow rate into the refrigeration effect. Okay, that means what? It is going to be m dot into H1 minus H4. This is going to be a refrigeration effect. Okay, and what is going to be the power input? Power input is also going to be the mass flow rate into W input. W input is what? W input is nothing but work done by the compressor. Okay, so m dot into H2 minus H1 is going to give you your power input. Okay, now we have been naming this chapter as refrigeration, but using the same cycle we can also build a heat pump. Okay, now heat pump is also a work consuming device, work consuming cycle. Okay, so that means what? In heat pump, only difference with the refrigeration is that here this is our required effect in heat pump. Okay, in refrigeration system this was our required effect or refrigeration effect. Okay, and in case of heat pump, this is going to be our heat pump effect, or you can say this is going to be our required effect. Okay, otherwise everything is going to be same cycle is going to act as a refrigerator also and heat pump also. Okay, but the thing is that has been asked in the question. Okay, so everything is going to be same, but if you now use requested to find what is going to be the COP of the heat pump, what you can say, you can again write the required effect. Okay, not the refrigeration, this one is refrigeration effect, but this is not required. Better I am writing HE, that means heat pump effect. Okay, divided by what? Divided by what is going to be your W input. Everything is going to be same. Only thing is that the denominator is going to change from this heat to this heat, so that we can turn the COP of refrigerator to heat pump. Okay, so if you want to find the heat pump, this is going to be that means the Q out you are required to find out. Okay, what is the amount of Q out or Q rejected? So from this analysis, what was the amount of Q rejected? It was nothing but H2 minus H3. H2 minus H3 was your amount of heat that has been rejected. Okay, to the thermal reservoir with higher temperature. Okay, now what is going to be the work input again? It is again going to be H2 minus H1. Okay, H2 minus H1 is going to give you the work done by work that has been consumed by the compressor, okay, or amount of work input. Okay, so this is going to be the COP of heat pump. Okay, so this is all that is related to COP. Now we are going to start with the vapor absorption refrigeration system. Okay, vapor absorption refrigeration system is same as that of vapor compression refrigeration system, but the only thing is that we are replacing the total compressor with an absorber, with a pump, with a generator, and one pressure releasing valve. Okay, now if you replace the compressor with all these four parts, then it is going to be converted into your vapor absorption refrigeration system. Okay, now in vapor absorption refrigeration system there are two things, okay, mixture of two things that previously it was only one working substance that has been running around the machine parts. Okay, now what is going to be there? Now it is going to be a mixture. There would be mixture of two things. One would be the refrigerant that is going to help you attain the lower temperature, and another thing would be absorber. Now how these two things will be acting while traveling throughout the cycles, that we are going to see now. Okay, now everything is going to be same as the previous one, but the difference starts from here. Now ammonia and water are the most famous and most well known duo of absorber and refrigerant. Okay, these two are the most popular mixtures. Okay, and these two are going to be acting as our working fluid now. Now the main difference with the vapor absorption refrigeration comes after this. Okay, now whatever refrigerant we were using in the vapor absorption, we do not know. Okay, but here we know. Here we know means what? We are taking the most famous one, NH3 and H2 as the working fluid, where NH3 is going to act as our refrigerant and H2 is going to act as our absorber. Okay, now as I have said, the difference starts from here. Whatever the substance that has been coming out from the evaporator is nothing but in gaseous form, and it is going to be the ammonia. Okay, after that there is going to be one absorber. Now whenever the NH3 passes through this absorber, this H2 catches them. Okay, this H2O catches them. That means now there is a mixture of ammonia and water. Okay, there is a mixture of ammonia and water. Now after that, NH3 and H2O goes in liquid form. Coming out from here, it is going to be completely liquid. Okay, as NH3 is now mixing with the water, now the thing that is coming out of the absorber is going to be completely liquid, and that thing is going to be pumped in by the pump. Okay, but the work done by pump is considered as negligible. Okay, because this work done by this pump is going to be negligible. Okay, or very less. Okay, so that we are converting into negligible. Now after the pumping in the liquid NH3 plus H2O, it is transferred into the generator. Okay, in generator what happens? We give a heat of Qg. Okay, we give an amount of heat of Qg. Now giving this heat, what is going to happen? There is going to be the mixture of NH3 and H2O. After giving heat, what happens? The NH3 is going to evaporate. Before the water evaporates, the NH3 is going to get evaporated. Okay, NH3 means ammonia. Ammonia is going to get evaporated, and it comes out of the generator. And the remaining water, okay, whatever the water is there, water that comes down through a pressure releasing valve to the absorber again. Okay, the water that is remaining after the evaporation of the NH3 or ammonia, the remaining water comes out through a pressure releasing valve. Okay, and after that it reaches the absorber again. Okay, now the gaseous NH3 is passing through the condenser again. Condenser means what? It is going to be converted into liquid, and heat is going to get rejected from the condenser. Okay, now whatever the ammonia that is coming would be in liquid form because it is passing through the condenser. After this, we are going to pass it through a throttling valve. Throttling valve means what? It is going to again expand the liquid and release the pressure. And since the pressure is released, that means what? Pressure is now less, and we have all known that if the pressure is less, then the boiling point also decreases. Okay, so at that time, after expanding, there is going to be liquid plus gas. Okay, the NH3 is again coming with liquid plus gas, and after that it is again going to get evaporated through this evaporator. Now while evaporator is acting, then this liquid, whatever the liquid is remaining now, is again going to be converted into gaseous. Then after that the total gaseous ammonia is going to come out of the evaporator. Okay, and this evaporator is again going to and that ammonia is again going to get mixed into the absorber with the water. Okay, so after that this cycle is going to get continued. Okay, so this is going to be the vapor absorption refrigeration system layout. Okay, now if you see, this is where heat is rejected, and this is where heat input is there. From the heat input to the system, from the space where we need to maintain the temperature. So there is what, this is also a heat input process. Okay, that means what, we are giving heat in two different ways and we are rejecting heat in one direction only. Okay, so that means via two paths we are going to give heat into the system, and via one path it is going to get released. This work done by pump is generally considered as negligible, until and unless it has been mentioned in the question. Okay, if it is mentioned in the question that this work that has been consumed by the pump is having this much of joule or this much of kilojoule, then only we are going to not neglect this. Okay, then we are going to accept these values. Okay, otherwise this is going to be considered as complete negligible work. Okay, so after that we will be going to the analysis of this vapor absorption refrigeration system. So this is going to be the basic layout for our VARS system. Okay, or vapor absorption refrigeration system. Okay, so now here there is no work interaction. Okay, because the work done by that pump is negligible. Okay, so now it is going to interact heat with three different directions. Okay, so one is TE, that means evaporation temperature. From evaporation temperature it is going to give away the heat of QE. Okay, and that heat is going into the system or the cycle. Okay, now in from the TG is the generator temperature. Okay, that means what, from the generator temperature an amount of QG is coming into the system, and the system is rejecting a heat to the temperature or atmosphere. Okay, so the atmospheric temperature is going to be T0, and the amount of heat it is giving to the atmosphere is going to be equal to the heat rejected. Now if you want to see the fast flow, okay, so fast flow is what, fast flow for a cycle is what, the heat interaction is going to be equal to the work interaction. Okay, the heat interaction is always going to be equal to the heat interaction. Since in this cycle there is no work interaction, even if there is a work interaction by that pump work is considered as negligible, so you can write it as 0. Okay, now what is going to be the heat interaction here from the first law? You are getting a heat of QG. Okay, plus you are going to get a heat of QE. Okay, this heat you are going to get from the generator, and this heat you are going to get from the evaporator, and you are going to reject one heat of QR. Okay, is going to be equal to 0 since the work interaction is going to be 0. Okay, so from this equation you can write QR is going to be equal to QG plus QE. Okay, so from this equation you can easily write QR, or the amount of heat that has been rejected is going to be equal to the total amount of heat that has been collected by generator and from the evaporator. Okay, so from this from the first law of thermodynamics for a cycle, we are going to get this. Okay, now what about the second law? Okay, now if you want to find out something from the second law, you have to remember what was the Clausius inequality statement. Okay, from the Clausius inequality statement, we have found that the cyclic integration of heat interaction by the temperature is always going to be less than or equal to 0. Okay, now if the cycle is going to be reversible cycle, then it is going to be equal to 0. If the cycle is irreversible, then it is going to be less than 0. So this was our statement. Okay, now from this statement, the cyclic integration of dq by t means what? If you add up all the terms by heat interaction divided by that corresponding temperature, okay, at which the heat interaction is going to take place, and you sum up all this, then you are going to get less than or equal to 0. So what is going to be the cyclic integration of dq by t term here? So first heat that has been getting interacted is Qg. At what temperature is it is going to get the interaction? It is at Tg. Okay. Plus this is positive because heat is getting added to the system. This is also will be positive. Okay, because it is also getting added to the system. So Qe is the evaporator heat that has been getting interacted at a temperature of Te. Okay, and there is one heat rejection process. What is that heat rejection process? Heat rejection process is nothing but Q rejected, and it is rejecting at atmosphere. So this is going to be less than or equal to 0. Okay, so this is going to be less than or equal to 0. Now this is your another equation. This is your one equation. Now from this equation we know that QR is going to be equal to Qg plus Qe. So if you replace QR with Qg plus Qe, then the equation that you are going to get is, it is going to be Qg by Tg plus Qe divided by Te, and we are separating this QR with the help of Qg and Qe. So you are going to get Qg by Tg minus minus Qe, that is T naught. Okay, this is T naught. Qg by T naught minus Qe by T naught, and that is going to be less than or equal to 0. Okay, that is going to be less than or equal to 0. So what we have done, we have kept this part same. Okay, but for this part we have separated this Qg. If you take minus common, it is going to be Qg plus Qe by T naught only. Okay, so same thing, we are just separating this, keeping the minus in mind, and there would be Qg and Qe. Now for the second step of this, what is going to be there? You can now take Qe common. If you take the Qe common from here, what is going to be remaining? If you take Qe common, it is going to be 1 by Te minus 1 by T naught. Okay, this is going to be the case. And again, now you can take Qg common. What is going to be the remaining when you take Qg common? It is going to be 1 by Tg minus of 1 by T naught, and that is going to be less than or equal to 0. Okay, so this is the case. Now what we are doing, we are going to take this part to the right hand side. Okay, so if you take this part to the right hand side, what is going to be there? 1 by Te. Okay, or you can simplify it directly. If you simplify it, you are going to get Te into T naught. Okay, and you are going to get T naught minus Te. After simplification of this, you are going to get this. Okay, and if you take this part to the right hand side, you are going to get Qg into, now this, if you are taking this to the right hand side, this thing will interchange, because if you take the positive to the right hand side, it will become negative. Okay, instead of negative, I am interchanging its places. Okay, so it would be 1 by Tg minus 1 by T naught minus 1 by Tg. This would be the case. Okay, now if you again simplify this, what would be there? If you again simplify this, you can get T naught into Tg. Okay, and you can get Tg minus T naught. Okay, after simplifying, I am writing directly after simplifying this and taking it to the right hand side, then this is the thing you are going to get. Okay, now from here we are doing some cross multiplication. That means we are taking Qg in the denominator here. Okay, so this is going to be Qe by Qg. Okay, Qg is going to be the denominator here, and from both these parts T naught and T naught is common. Okay, so we are cancelling out T naught. Okay, so we are again cross multiplicating this at that side. So at that side, what is going to be the remaining? Tg minus T naught divided by Tg. Okay, and multiplied by, if this goes to the right hand side with multiplication, okay, or cross multiplication, you can say the remaining thing you are going to get is Te divided by T naught minus Te. This is the thing you are going to get. Now Qe is what? From this vapor layout, Qe is the amount of heat which we need to take out so that we can maintain a temperature of Te. Okay, QE is the, you can say directly Q is the refrigeration effect. That means this is the amount of heat we need to take out so that we can maintain a temperature of T. Okay, and what is QG? QG is nothing but Q in or Q input. Okay, because to run a refrigerator we need to give some work. Since the work here is negligible, the another work or another energy which we need to give in as input is going to be the generator heater. Okay, this heat is going to be acting as input because that is the amount of heat we are going to give. Okay, this is the amount of heat which we are going to give to the system. Okay, so this is going to be so now what is going to COP? COP is the whatever output you are going to get. Okay, COP is the whatever output you are going to get. Output is what? Nothing but the refrigeration effect. Okay, and what is the input we are going to give? This is nothing but Q in. So refrigeration effect is what? Refrigeration effect is nothing but whatever the heat that has been taken out from the evaporator. Okay, and Q in, the input heat is what? Nothing but whatever the heat you are going through generator. So QE by QG is going to be your COP. Okay, so this thing is going to be your COP. So COP is what? COP is less than or equal to Tg minus T0 divided by Tg. Okay, and Te divided by T0 minus Te. Okay, so this is going to be your COP. Now they are saying that COP is less than or equal to this term. Okay, COP is going to be less than or equal to this term. Okay, that means what? The COP can be less than this, or it may be equal to this, but it can never go beyond this. Okay, so COP can be less than this value, or it can be equal to this value, but it cannot go beyond this value. So from here we can write what is going to be your maximum COP. So in place of maximum COP, that means what? At max, how much value can COP achieve? How much value can COP achieve? It can be this value. Beyond this value it cannot give. Okay, that has been proved. Okay, so you in place of COP max you can write that the COP max is nothing but Tg minus T0 divided by Tg multiplied by Te divided by T0 minus Te. So this is going to be the formula for COP max. Okay, and this formula is very important, keeping gate in mind. Okay, for a gate point of view, this equation is going to be very important. So from the VARS, this is the equation or question from this equation related to this equation comes mostly. Okay, so this thing is going to be very important, and this is the complete analysis of the VARS refrigeration. Okay, so now we are going to see effect of variation of properties on the performance of vapor compression cycle. Okay, so we are going to change the properties, and we are going to see whether the performance are going to increase or decrease. Okay, so now the case 1. Okay, for case 1 it is decrease in the evaporator pressure. Okay, so this is going to be the TS diagram, and this is going to be the pH diagram. Okay, so if you decrease the pressure, then it will come somewhat like this. Okay, it will come somewhat like this. Okay, because we are decreasing the pressure now. Okay, similarly here if you decrease the pressure, it would come somewhat like this. Okay, so seeing both this diagram, what we are going to see, this is 2, this is 2 dash, this is 1, and this is going to be 1 dash. Okay, so seeing this, from 1 dash to 2 dash is going to be our new work consumed by the compressor. Okay, or you can say work input. That means work input by the compressor is now going to increase. Okay, same here. Previously it was from there. Okay, 2 minus 1. Now it has gone from 1 dash to 2 dash. This is going to be the enthalpy difference now. Okay, this is going to be the enthalpy difference now. Previously the enthalpy difference was only this much. That means what? From the diagram we are seeing that the work input, okay, work input is going to increase now. And what about the refrigeration effect? Refrigeration effect previously was from here to here. Now it is decreased from here to here. Okay, so that means what? Again, if you can see the refrigeration effect, previously it was from here to here. Now it has decreased from here to here. Okay, previously suppose this is 4 dash and this is going to be 4 and this is going to be 1. So 4 to 1 is bigger than 4 dash to 1 dash. Okay, that means what? Now the whatever the refrigeration effect was there, it is now decreasing. Okay, if you decrease the evaporation pressure, so what is going to be the COP? For COP it is nothing but refrigeration effect divided by the work input. Okay, so now work input is increasing and it is going to decrease. Okay, so the denominator is increasing and numerator is decreasing. That means what? The COP is also going to decrease now. Okay, so now if you decrease the evaporator pressure, your performance is going to decrease. Okay, so the second case is increasing the condenser pressure. Okay, now you are going to increase the condenser pressure and you want to see what is going to be the effect. Now 1 to 2A was the previous one. Now if you increase the pressure again, now this is going to be your new 2 dash and this is going to be your 3 dash, and after that you are going to come like this. So this is going to be 3 dash. Similarly for pH diagram also, if you increase the pressure, it will go like this and it will come like this. This will be your new pressure when you are increasing the condenser pressure. So this is going to be your 2, this is going to be 2 dash. Similarly here also you are seeing that work input is going to increase and refrigeration effect is again going to decrease. Refrigeration effect is again going to decrease. So refrigeration effect is decreasing here, work input is increasing here, so the COP is obviously going to decrease. Okay, this was our second case. Now we are going to the third case, that is superheating. What will be the performance of the VC cycle or vapor compression cycle when superheating is done? Now what is superheating? Superheating is nothing but if you are adding heat, even if the complete liquid has been converted into vapor, then also if you are adding heat, then this steam is going to be getting superheated now. Okay, so this is the exit of the evaporator. After coming out at this line, this is the saturated gaseous line, that means here the complete vapor has been converted, okay, or the complete liquid has been converted into vapor. Now if you are again superheating it, now after coming out from the vapor dome, the constant pressure line is going to be there, and we are also going to add heat at constant pressure only. Okay, so after superheating, this is going to be your new compressor line, or you can say this is going to be 1 dash, because whatever the vapor that is coming out from evaporator, it is again heated and it is reaching point 1 now. Then after that we are compressing it isentropically, so it is reaching point 2 now. Okay, so from here what you can see, now work input is going to increase now. Similarly from here also, now you are superheating this. Okay, superheating this means this is going to be your new 2 dash and this is going to be your new 1 dash. So from here you can easily say that work input is going to increase now. Okay, work input is going to increase now. Now what is going to be the refrigeration effect? Refrigeration effect, previously it was this much, now it is going to be this much. So refrigeration effect is also going to increase. Here also same, previously the refrigeration effect was this much, now it has increased to this much. Okay, now refrigeration effect is also going to increase. Now what about COP? COP is what? Nothing but refrigeration effect by, now both are going to increase. Now both are going to increase. So what will happen to the COP? Now COP, the performance is going to increase or decrease is hard to tell, because this COP, in case of superheating, this COP performance is dependent upon the refrigerant. Okay, now if you use the NH3, if you use NH3, then with the superheating the COP decreases. But in place of NH3, if you use the refrigerant R12, the COP increases. Okay, so here the performance it may increase or it may decrease also. Okay, this cannot be sure, or we cannot be sure about this one. This is completely dependent upon the refrigerant we are going to use. Okay, so the next case is our subcooling. Okay, so what is subcooling? If the products, okay, previously it was superheating. Superheating was the products coming out of the evaporator and we are heating those products again. Now subcooling would be the process, whatever the products that has been coming out of the condenser. Condenser means after phase changing, okay, from gaseous to liquid, it has been changing in condenser. So after converting it into complete liquid, if you are pulling it apart, okay, if you are pulling it again beyond its saturated liquid line, then this is going to be known as subcooling. Okay, that means what? the 2 to 3 is going to be condenser that has been working isobarically. Okay, isobarically. So at constant pressure, if we are again going to, because of before, after coming out from the after coming out from the vapor dome, the constant pressure line is this one. Okay, so now if you are going to cool this apart, okay, or if you are going to cool this apart, then what will happen? This is going to, or this is going to be your new diagram. Okay, this is going to be new diagram. So what is happening after coming out from the condenser, we are pulling it apart, then again isenthalpically it is coming to 0.4, and after that it is going to 0.1 again. Okay, so this is going to be 0.4 dash and this is going to be a 3 dash. Similarly here what will happen, it will be cooled. Okay, and after that this will be 3 dash and this is going to be your 4 dash. Okay, so what is happening here, you are pulling that liquid apart, whatever the liquid that has come out of the condenser. Okay, that liquid has been cooled again. Okay, that liquid has been cooled again, and after that it has been passed through the evaporator again. So what is happening now, if you can see, the work input is going to be constant, 1 to 2 is constant, nothing is hampering the work that has been consumed by the pump or the compressor. Now refrigeration effect is now increasing, 4 dash to 1. Previously it was from 4 to 1. Now it is from 4 dash to 1. Similarly here it was from 4 to 1. Okay, now it is from 4 dash to 1. So refrigeration effect is obviously increasing. So if refrigeration effect is increasing and this is going to be constant, then COP is going to increase obviously. Okay, so from here we are studying these 4 cases. Okay, to know what would be the changes in properties is going to hamper the performance of the VC cycle or not, we are going to see from these 4 cases. Okay, so this from up to here the refrigeration has been done.